Here. So yeah, it's going to be a talk about continuous gravitational waves. My name is Covas, and I'm a postdoc at the Max Planck Institute for Gravitational Physics in Hanover. And this talk is going to be a very brief summary of this paper. This is the title of the paper that came out about a couple of months ago. So yeah, I'm the second author of this paper, and Jan Ashok is the first author of this paper, but she couldn't be here, so yeah, I'm presenting this on her behalf, and also we collaborated with Reinhard Briggs and Mayra Sandapapa. So yeah, this talk is going to be again a very brief summary of this paper. I will not have time to go into the mathematical details of our derivation, or I will not have time to explain everything, so please, if you have questions, ask me, or have a look at the paper for more details. So I will give first an introduction of what this new method is and what targeted searches are. Then I'm going to talk about the tests that we did to test this new method, to carry out these searches. And then I'm going to talk about the search that we did for this specific pulsar. Okay, so let's start. You heard a bit about this already before, but I will repeat a bit again. So you can see here this plot, which shows the different types of continuous gravitational wave searches that use data from ground-based detectors like advanced LIGO. So on the y-axis you have the computational cost, and on the x-axis you have the knowledge that we have about the source. So you can see that targeted searches are here on the lower right part of this plot, and this is the searches I'm focusing on in this talk and in this paper. So targeted searches look for continuous gravitational waves from neutron stars that we already know of, so from known pulsars. So these are neutron stars that have been detected with radio searches or X-ray searches. And we already have information about their rotational frequency, their sky position, or if they are in a binary system, we also know the parameters that describe this binary orbit. So because we already have all of this information, there is a massive reduction in the size of the parameter space that needs to be searched. And these searches can do a fully coherent combination of all of the data that is available. And because of this, these targeted searches are the most sensitive type of continuous gravitational wave searches. On top of that, another interesting fact is that because the presence of a neutron star is already assured, even a non-detection or a null measurement is already also directly informative about the gravitational wave emission of the source. Okay, some very brief details about the signal model, the signal that we assume and that we are searching for. As already explained before, we are looking for continuous gravitational waves from a fast spinning neutron star, which has a varying mass quadrupole. So in the absence of precession, we expect the continuous gravitational wave signal to be at twice the rotational frequency of the neutron star. So the signal that we expect in the detector is given by this equation, where you have the two different polarizations of the gravitational wave. So F plus and S cross are the so-called antenna pattern functions of the detector, which describe the sensitivity of the detector to different directions of the sky, and also to a different polarization angle. And the H plus and H cross waveforms are given by these equations, and they are the two waveforms that we search for. You can see that they are dependent on many different parameters and on the unknown signal phase evolution. So this signal model that we assume, it depends on a certain number of parameters, and we can divide them into different peak groups, the so-called amplitude parameters and the so-called phase evolution parameters. So I already talked about these phase evolution parameters, which are the ones defining the phase evolution of the signal. So you have the frequency evolution, the sky position, and if the system, if the neutron star is in a binary orbit, the parameters defining the Keplerian binary orbit. As I was already saying, in a targeted search, all of these phase evolution parameters are known, and we only need to focus on the 4 unknown different amplitude parameters, which define the signal. So we have the gravitational wave amplitude, we already talked about it in previous talks, the inclination angle, iota, the polarization angle psi, and the initial phase of the signal phi 0. Okay, so in this paper we are proposing a new method, a new pipeline to carry out these targeted searches for continuous gravitational waves. So previously, before this new paper, only a single Bayesian pipeline existed called the time domain method. And yeah, I think it's important to have more than one pipeline to be able to carry the same type of searches, because they have different advantages and disadvantages, and yeah, so it's important to have more than one pipeline. So what we do in this new paper is that we introduce a new expression and a new implementation of the continuous wave signal likelihood function. So you have your two different hypotheses about the data. So one is the noise hypothesis, where you assume that the data only contains Gaussian noise. And then you have the signal hypothesis, where you assume that the data contains Gaussian noise, but also a continuous gravitational wave signal. So yeah, so in this new paper we proposed a new implementation of this likelihood function based on the well-established and computationally efficient F-statistic framework. So what we do is that instead of analytically maximizing the likelihood ratio over these 4 unknown amplitude parameters, that this is what the F-statistic is, instead of doing this analytical maximization, what we do is set up priors over these 4 unknown amplitude parameters, and then we use a stochastic sampler like Dynasty to search over these prior ranges on these 4 unknown amplitude parameters in order to obtain posterior distributions over these 4 amplitude parameters. Besides this likelihood over these 4 unknown amplitude parameters, we also propose a new likelihood where the initial unknown phase, phi 0, has been analytically marginalized, so only 3 amplitude parameters remain. And this helps us in order to overcome some degeneracies that exist between the phi 0 and the polarization angle of the signal. Yeah, just some final words about this new pipeline that we proposed. In this paper, we only talk about obtaining posterior distributions over these 4 unknown amplitude parameters, but this pipeline is general and can be used with any combination of the parameters that describe the continuous wave signal. And yeah, so you can, besides the amplitude parameters, you can also search over the phase evolution parameters. I will skip this. Okay, and now I will talk a bit about the tests that we did to check that this pipeline is properly working and recovering the signals. So yeah, this is the typical corner plot. So what we do here is that we inject one single signal without noise, and then we use our new method to obtain the posterior distribution over the 4 amplitude parameters. So in orange here you can see the true values of the parameters of the signal, and the blue shaded regions show the recovered posterior distribution. And you can see, this is a very basic test, but you can see that the maximum of the posterior, the mode of the posterior, coincides exactly with the parameters of the signal, which is an indication that our pipeline is working as supposed. We also do this for the likelihood that has the initial unknown phase that have been analytically marginalized. So here you only see the 3 remaining parameters, and then we compare it to the full likelihood, to the posterior of the full likelihood, where the phi 0 has been here projected out, and we observe also that they are basically the same, which is also a nice test. After this, what we do is to produce PP plots. So before we had a single signal without noise. Now what we do is have 10,000 signals added to Gaussian noise, and we obtain these PP plots. So on the x-axis we have the credible interval, different credible intervals, and on the y-axis we have the fraction of events or fraction of injected signals that are recovered in each of these credible intervals. And you have each different color shows one of these 4 or 3 different parameters. So what we expect here is to have a straight line. This is the sign that everything is working as it is supposed to. And we observe here also that it works very well. We also calculate p-values shown here in the legend, and the higher the better. And yeah, we also see that it works properly. As a final test, we also use Harrow injections. So as Benjamin already explained, these Harrow injections are not software signals added in the software, but they are actual signals added by moving the mirrors with auxiliary lasers, so in the actual interferometer. So these tests are nice because they're using actual real data from the advanced cycle detectors. So we ran our pipeline on the 15 different Harvard injections. Here I'm showing 2 different examples. And we basically say that the parameters of the Harvard injections are recovered, the pulsars recover the parameters of the injections, of the Harvard injections. Okay, very quickly, let me give you some words about the search that we did for this pulsar, J1526. So this pulsar was discovered recently in a joint survey by Trapum and Fermilab, and the timing solution was derived from 13 years of Fermilab data, which overlaps with the observation runs from advanced LIGO. So the search that we did is done using a fully coherent combination of data from the 01, 02, and 03 observation runs of the advanced LIGO detectors. And yeah, so no CW signal was detected with both the full and the marginal likelihood. And we obtained a 95% upper limit on the gravitational wave amplitude of 6.7 times 10 to the minus 27, which is a factor of 10 larger than the spin down upper limit of the pulsar. So even in the first place, we were not really, we would have been really surprised if we would have detected a signal. So here you can see the posterior distributions for the actual search with both of the different likelihoods. And the important axis here, the important column to look at is the leftmost one, which shows the posterior and the gravitational wave amplitude. And you can see that the mode is basically on the leftmost side of our prior, which is basically saying that there's no signal and this is compatible with volume noise. Skip this. Okay, just some future work that we want to do. Our pipeline has some limitations due to using the statistic framework, so we need to do some studies on how to overcome this. Also, here we just studied, as I said, we assumed that the phase evolution parameters like rotational frequency or type position were perfectly known, but of course they have some uncertainty too, so we need to study how to expand these to include them. I also want to study more complex signal models, which have continuous gravitational signal and more than a single frequency, and also applying this framework to search for more pulsars. Just finally, I want to say that for these targeted searches, it's very important to have timing solutions from electromagnetic searches. And yeah, this is what allows us to do these kind of searches, which are the most sensitive ones. If you want more information, this is the paper which describes all of this. Thank you very much.
Thank you, Fred. Any questions?
It's really not a lot because for the actual search it required like hundreds of seconds. It's really fast. I think likelihood evaluation is on the order of, let's say, 10,000. So 10 to the 4, a few 10 to the 4. Yeah, it's really fast. Like in 100 seconds you get the results from the search. No, so for the PPPOs it's only, no, these are only simulated signals on top of Gaussian noise. For the Harvard injections you only have 15 of them, and also we don't know what is the priority distribution that was used to draw the parameters of them. So we cannot do PP plots.
I see.
So as I'm saying, you cannot do PP plots because you don't have so many and you don't know the prior distributions, but also those are with real data, so you have non-Gaussianities, or sometimes the actuation function that drives the laser to create this Harvard injection doesn't work properly.
I see.
So you have more real-world stuff, but yeah, you don't expect to see as good a behavior as the one in the...
Right.
Any last quick question?
I would say that the main advantage is that you can properly take care of the prior distribution. So, for example, I didn't go into detail with this, but you have the neutron star has the rotation axis, right? And we assume that it is isotropic. So, because we don't have more information about this, and we expect that over our galaxy, neutrons are going to be the rotation axis is going to be isotropic. So we can set up priors in the inclination angle and polarization that reflect this, but with a frequentist search, you cannot correctly incorporate this. And if your signals are actually distributed according to the prior that you're using, the Bayesian search is always going to be more sensitive.
Thank you. Thank you.